In this segment, we'll look at floating point computation in assembly at ARM floating point opcodes and special registers, and we'll look at the format and structure of floating point values. So let's start by showing how floating point values are represented in binary. And first, let's do a reminder of how binary fractional values work. We did this a little in earlier topics, but a reminder here. A decimal floating point number like, say, 3.1416 uses fractional place values, of course. And as we move to the right, the value of each decimal place has 1/10 the value of the one to its left. So tenths place, hundredths place, thousands, 10,000ths place. The pattern continues past the decimal point. As you know, this allows arbitrarily precise representation of a fractional value as you add more fractional digits. And all the rules for counting, carrying, adding, and so forth extend naturally to the fractional digits. 0.109 plus 0.141 is 0.250, and that's as easy to compute and follows the same rules as 109 plus 141 is 250. Precisely the same thing can be done with binary values, but with the obvious difference that place values reduce by a factor of 2, not 10, as we move to the right. So we add bits below the ones place after what we might call a binary point rather than a decimal point. E.g., we could write 1.1101 like that. Each place value to the right of the binary point has 1/2 the value of the one to its left. So we have the 1/2 place, the 1/4 place, the 1/8 place, 1/16 place, and so on. So, for instance, 0.1 alone represents the value 1/2, 0.01 1/4, 0.11 would represent 3/4, and 0.1101 actually represents 13/16. So question 1, let's translate, please, the following binary values into their equivalent decimal form. 0.101, 11.011, and 11.111. The answer here is that 0.101 is 1/2 plus 1/8, or 5/8. Or if you like, 0.625. And then 11.011 is 3 plus 1/4 and 1/8. So we would have 3 and 3/8, or 3.375. And then 11.111, again 3, and now 7/8, or 3.875. Decimal floating point numbers are used to represent a huge range of values, from the mass of an electron to the mass of a universe. In practice, however, we know any value only to a limited accuracy. So a given floating point value has only a certain number of non-zero digits. If we write out very large or very small numbers entirely, there are a lot of zeros, like this. Instead, we use scientific notation, typically written with a mantissa between 1 and 10 in value, and an exponent of the base 10. And that implies a shift of the mantissa left or right by some number of digits. So an electron's mass instead is 9.1 times 10 to the minus 31st power kilograms. And the mass of the universe is 3.1 times 10 to the 52nd power kilograms. Let's move that over a little bit. And the mantissa, 9.1 or 3.1, determines the accuracy. The exponent, minus 31 or positive 52, determines the size range. More mantissa digits provide greater accuracy, if I had more digits here, and more exponent digits provide greater range. Typically, the mantissa digits are more important since 2 or perhaps 3 exponent digits are sufficient for all practical purposes. Now, scientific notation also works in binary, with the obvious change that the mantissa is in binary and the exponent is a power of 2, not 10. So we might write 13 or 1101 as 1.101 times 2 to the third power. As in decimal scientific notation, the power of 2 has the effect of shifting the binary point to the right or to the left. And as in decimal scientific notation, the mantissa has exactly 1 digit to the left of the binary point. But note, in base 2, that means the mantissa is less than 2. It's always 1 point something or other. Question 2. Translate the following values into binary scientific notation. 28, 5.25, 0.0625. And note, by the way, 0.0625 is 1/16. So, if you've thought about those a bit, 28 comes off, or works out to 1.011, no, sorry, 1.11 times 2 to the fourth power. 5.25 is 1.0101 times 2 to the second power. And 0.0625 is 1.0 times 2 to the negative fourth power. And if it helps clarify why that is so, remember that 28 is 11100. That's 4 plus 8 plus 16 is 28. And then shifting the decimal point to 1.11, we have 2 to the fourth power. Likewise, 5.25 is 101.01. And shifting by 2, we get 1.0101 times 2 to the second power. 0.0625 is 0.0001, and so that equals 1.0 times 2 to the negative fourth power. Any floating point variable, like a C double, is a binary scientific notation number, with some of the variable bits devoted to the mantissa, some to the exponent, both in base 2. The organization of bits within the number is so important that there is a nearly universal standard for it, the IEEE floating point standard. This standard divides the bits of a floating point variable into 3 parts, with the number of bits per part varying by the number of bits in the entire variable. For a 64-bit variable, which is the most common, for instance a C double, the parts are a sign bit, then 11 exponent bits, and then 52 mantissa bits. Quite a lot devoted to the mantissa. Each of these parts has an interesting minor point attached to it. The sign bit, for instance, indicates the sign of the entire number, but the interesting point is that it's not a 2's complement sign. Floating point values use sign magnitude. So the sign bit is simply a 0 if the number is positive and a 1 if it is negative. The exponent and mantissa represent the absolute value of the number either way. The exponent gives a power of 2 as an integer, and its interesting point is that it's not a 2's complement value either, despite needing to represent negative exponents. 11 bits can represent unsigned values from 0 to 2048, 2047 actually, but the exponent is an excess 1023 number, which means it's a positive unsigned value, but it's equal to the exponent value plus 1023. An exponent of 1, for instance, is represented by 1024 in the exponent bits, or 1 and all zeros. Thus, an exponent of 2 would be a 1, all 1, like that. And an exponent of -1 would be 0, 1, 1, 1, 1. That's 1023 minus 1, like that. So we'd have an exponent of minus 1. This is certainly an odd way to represent the range from negative 1023 to 1024, but it is preferred for hardware design reasons beyond the scope of this discussion. Question 3. What are the exponent bits for the exponent values 0, minus 8, and 42? The answer there? Well, the 0 would be exactly 1023, or a 0 in all ones. The minus 8 is 1023 less 8, or 1015, which turns out to be this value here. And the 42, 1023 plus 42 is 1065. And that turns out to be 1 like that. The mantissa represents or occupies the majority of bits here. And its interesting point is that only the bits after the binary point are stored, because in a correctly normalized binary floating point value, the mantissa always starts with 1 point. So the 1 to the left of the binary point is simply assumed. So a mantissa of 1.101 would be stored simply as 101 and then a bunch of zeros. Let's try a few examples with the 64 bits of the floating point value broken into sign, exponent, and mantissa fields. So, for example, this is 5.25, and that is 1.0101, as we determined earlier when I think we had that value. Yeah, right there, 0.0101, sorry. And the mantissa has just the fractional part, 0.0101. The number to the left, the 1 to the left of the binary point, is simply assumed. And this exponent value here is equivalent to 2, and the sign is a positive. Or, if you like, minus 23.25, which we don't actually have as an example. Fill that in a little better there. Minus 23.25 is negative 10111.01, or negative 1.011101 times 2 to the 4th power, or a sign bit of 1, a exponent of 1027, thus 4, and the mantissa again having only the digits or bits after the binary point, 0.1875 is 0.00011, or 1.1 times 2 to the minus 4, or here an exponent of 1023 minus 4, so that particular binary pattern, and then merely a 1 for the mantissa, again showing only the bits after the binary point. And then perhaps most interesting, 0.2 actually works out to 0.011011 repeating over and over again, or 1.1001100 repeating times 2 to the minus 3rd, or positive minus 3 as the exponent, exactly 1020 in fact, and then the mantissa with that repeating pattern going on and on for 52 bits. The last one is interesting in that 0.2 is a repeating fraction in binary. Whether a fraction is repeating or not is not an inherent property of the value. For instance, the repeating decimal fraction, 1/3, is simply 0.1 in base 3, since the place value after the trinary point would be 1/3. The value 1 over x repeats if x has any prime factors that are not prime factors of the base. In decimal, that means that x may have only prime factors 2 and 5. In binary, it may have only 2 as a prime factor. So 1/5, 1/10, 1/20, etc. are all repeating fractions in binary. Those 52 bits of mantissa make a little more sense when you consider such cases. Question 4. Write out the full binary values, including the sign, exponent, and mantissa, for minus 32.5 and 0.375. And if you've thought that through, the answer is minus 32.5 is negative 1,000.1, or 1.501 times 2 to the 5th power, or 1 and then 1028. And the mantissa, again dropping that 1 point, just the 5 zeros and 1 here. 0.375 is 0.011, it's 3/8, or 1.1 times 2 to the negative 2, or positive sign, right there, 1021 as an exponent, and then just the 1 and all zeros after that for the mantissa. And then just kind of a fun question to throw in when we're talking about bases. Question 5. We use base 10 simply because we have that many fingers. If we were choosing a base from scratch, base 12 would be better. Why is that? The answer is 12 has more factors, and thus more fractions would be non-repeating. 1/3, for instance, is 4/12, and thus 0.4 in base 12. Indeed, base 60 would be even better, since 2, 3, 4, 5, and 6 divide it evenly. This is why we see it as a value in time units, for instance, the number of minutes per hour and seconds per minute. Floating point values come in different sizes. In particular, there's a 32-bit or single precision version of the IEEE format that has 1 sign bit, 8 exponent bits, and 23 mantissa bits. Thus, single precision computation is generally faster, and the values take half as much memory. But single precision floating point is quite imprecise. 23 bits of mantissa may seem like a lot, but they are equivalent to about 6 or 7 decimal digits of accuracy compared to the 15 to 16 digits you get by a 52-bit mantissa. 6 or 7 digits are sufficient for approximate computations, and in particular for many computer graphic computations, but any serious scientific work requires greater precision. There are also, to be complete about it, larger floating point values, for instance, for 80 bits or even 120 bits, all with IEEE formats like that for double precision. The additional bits are almost all devoted to the mantissa to increase accuracy. In the next segment, we'll look at how floating point operations are done in ARM.